So we are talking about refraction, and I'm going to do my best to sort of explain refraction to you. And so refraction is light has a different speed as it travels through different materials, and this causes light waves to change direction when crossing from one material to another. Okay, so let's see if we can do something that kind of shows what I want to see. So we're going to have a surface here, and so this is a surface, and on this side is going to be air, and on this side is going to be glass. And we're going to say that my light coming in, I have light waves that are traveling like this. And so what I'm doing is I'm creating light waves that are propagating down the page. And we'll call that good. And so these are light waves with lambda equals 3 centimeters. And so these light waves are going to go down the page like this, and I'm going to draw them as rays now. And then a funny thing happens when they get to the when they get down here. A funny thing happens is that they slow down, and so instead of moving at 3 centimeters between the lines, they're now going to slow down and they're going to move at 2 centimeters per line. So what I'm going to do is I'm going to mark every 2 centimeters. So where that crosses, I'm going to line it up so right now it's 3 on this side, 3 centimeters of separation, and on this side I'm going to do 2 centimeters of separation to show that it's slowing down. And this is just kind of you know, right now there's some physicist who's watching this who's going, oh my god, he's getting it totally wrong. I'm not getting it totally wrong. I'm just sort of avoiding some of the thornier details. And so, once again, under my right hand, the light wave is going with a wavelength of 3 centimeters, and then under my left hand, it's going at 2 centimeters. And so now what I'm going to find when I connect these dots is I get, let's see, so this one connects up, let's see, so I gotta call this 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6, 7. Okay, so this line of dots makes a wave front like this. So the 6s are all together, the 5s are all together, the 4s are all together, the 5s it should be continuous. I'm sorry, I should redraw the 5s. And I redraw those 5s. More like this. And then the 3s are all together. And so what you see is that at the surface, here the waves are going this way. The waves are going this way right outside the air, and then when they hit the surface they bend. And so right now overall, if I grab my protractor, which I kind of buried in all my gunk, let's see, let's do it right there. My new wave is going out like this. My old wave came in something like that. So because the wave slowed down when it hit the surface, it bent. And what we do is we create a normal to this surface, and again I'm making just sort of a real approximation of the actual physics. And so this is my normal. Everything's really getting confusing, I know. And I'm going to say that my angle is coming in at 37 degrees. And it's going out at 21 degrees. And so then what I have is a very quick sort of look at Snell's law. I have n1 sine theta 1 is equal to n2 sine theta 2, and I'm just throwing this out here right now, but we're gonna talk a lot about this. And roughly speaking, if I have I should have that the sine of 37 over the sine of 21 degrees is about, well, it's 1.6, it's 1.7, but it should be approximately 1.5, which is the ratio of 3 centimeters to 2 centimeters.